And we're looking now at this extreme value theorem. But before we look at the extreme value theorem, let's go back and let's talk about what it means to be a maximum value or a minimum value. And in this case, we're going to look at absolute maximum and absolute minimums. And so by definition, it says let f be a function with a domain D. Then f has an absolute maximum value on D, that domain, at some point C, if we can say f of x is less than or equal to f of c. So that y value is the biggest y value at x equals c, which is f of c, for that whole function f of x in that domain D. We can say that it has an absolute minimum value on D at c if f of x is bigger than or equal to f of c. So that y value at f of c in this case would be the smallest y value we would get back if we plugged in every value of x in that domain. So sometimes a function may or may not have an absolute max or an absolute min. For instance, if we looked at, let's just say, a parabola. Well, it depends on what way your parabola is facing and what our domain is. But if we had some parabola like this, let's just say, and we were looking at our domain is from negative infinity to infinity. And I was looking to see if there was any absolute maximum or absolute minimum for this function f of x. Notice that we have an absolute minimum, and the absolute minimum occurs when x is 3, but we say the absolute minimum is the y value. So our absolute minimum we get back is 2. So when x equals 3, this is going to give us back our smallest y value on this graph. And so we can say that this is an absolute minimum of f of x. So we have an absolute minimum of x equals 2. I'm sorry, not x equals 2. We have an absolute, sorry, we have an absolute minimum of 2 when x is equal to 3. So notice that because our domain is negative infinity to infinity, notice there's no x value that will give us the highest y value, because that continues to shoot upwards and it never has one biggest y value in there. So in this case, there's no absolute max. Well, let's say we had the same picture, but in this case, we limited our domain. So let's say we had, I don't know, our domain here is one, 2, 3. So if I look at that, let's just say that that is 4. So if I look at that, that's really the only piece I'm looking at there is when I have 1 here, I have 4. And it's coming down. And at 3, I had 2. So we're only looking at this piece in here of that f of x function. And so since we've limited the domain and it's on a closed interval, this is what our extreme value theorem is bringing us to, this actually has an absolute max and an absolute min. So there is a highest value that we're hitting on this graph, right? And that is our f of 1 value, which is 4. So we have an absolute max of 4 at x equals 1. And if we look at it right here, our smallest y value that we get back is f of 3, which gives us a y value of 2. So we have an absolute min of 2 at x equals 3. If we limited our domain, let's say, but this time, let's just look at one more example. Let's say it wasn't a closed interval. So in this case, our example above, x included 1 and 3. But let's say maybe it was including 1, but it stopped at 3 or getting really, really close to 3 on that left-hand side. So not really including 3, strictly less than 3. So we would have pretty much the same graph, except this time here, we would have an open circle instead of a closed circle. And if we have an open circle here, we actually don't have an absolute minimum, because if you say, okay, well, my absolute minimum here, right, is, let's say, oh, well, I'm getting closer and closer, and we could say the limit as x is approaching 3 from the left is equal to 2, but f of 3 doesn't exist because it's an open circle. And so I could say, okay, well, I think that 2.01 is the smallest y value. Well, you could come in and say, no, I can get even closer to that x equals 3. That would give me a y value that's smaller. And we could keep playing that game forever. And so there's no value in there that gives us an absolute min if we don't have that closed interval on our domain. So we do have an absolute max. Again, a 4 at x equals 1, and that's because it's closed in here, and there's no absolute min. So let me see if there's any question, and then we'll jump into the extreme value theorem. Okay, so we have this extreme value theorem in front of us, and what this extreme value theorem says is the following, but before I state it, so there's conditions for this extreme value theorem. So we need to make sure our conditions hold when we're looking at these examples, or if we want to use this theorem. So first of all, if f is a continuous function on a closed interval AB, okay, so f has to be continuous, and in this case, for this extreme value theorem, it does have to be a closed interval, some domain that includes the endpoints of our x values on the domain. So then f attains both an absolute maximum value, capital M, and an absolute minimum value, we're going to call it little m, in the interval of our domain that we're looking at from A to B. Okay, so that is, there are numbers x sub 1 and x sub 2 in AB, with f of x sub 1 equal to our minimum and f of x sub 2 to equal to our maximum. And we should know that our little m, the minimum, is less than or equal to all y values on our function f of x, which is less than or equal to the maximum value, that maximum y value for every x in AB. Okay, so if it's a closed interval and it's continuous, it has to have an absolute max and an absolute min. If it's not a closed interval, then it may or may not have an absolute max or an absolute min. And so let's look at the following example. And in these examples, we want to determine whether the function has an absolute extrema or extreme value on AB, then explain how the answer is consistent to that theorem we just talked about. So if we were looking at number 1 in here, this graph h of x. So first of all, I can see that we're going to have a smallest y value. So notice that our smallest y value in this case occurs at C sub 2. So if I go over here, that's the smallest y value that I hit. And then if I look at my graph, it looks like the highest y value I hit here is at the end value of my domain at x equals b. And this would be my f of b. So this is our absolute max. And our absolute min. Okay, so the extreme value theorem held true again because it was a continuous function on some closed interval. So same idea here for number 2. So number 2, notice that our function, this is a continuous function, and because my endpoints are closed circles, that means it's stopping there, so it's on a closed interval. And if I look at my smallest y value on my graph, it looks like it's occurring at b. And so my y value, which is the absolute min, is f of b. And the highest y value I'm hitting is when x is c. And that absolute max value is f of c. But if we jump down to problem 3, notice that this isn't a closed interval. We have our domain in this case is all values from a to b, but not including a and b. And that we can see that because of those open circles there. And so notice there's no smallest y value that we're getting back because of that. But we do have a value right here when x is c, that's giving me the highest point on the graph, and it's defined. This is a continuous function. So f of c is our absolute max. And there's no absolute min. So number 4, this is not a continuous function. So the extreme value theorem doesn't hold true, but that doesn't mean that it doesn't have an absolute max or absolute min. The problem is here that we have an open circle here. And so we don't have an absolute max that was closed. That's where an absolute max would be, but we don't. We can get closer and closer to whatever this f of a value would have been. And so we'll always get there's an infinitesimal number of things that will keep on being bigger and bigger. This is an open circle here, so there's no absolute minimum here. And so this has no absolute max or mins.
So the theorem doesn't hold true for both 3 and 4?
Right. Right. So extreme value theorem doesn't hold true.
Well, it still holds true. It just doesn't apply there, right?
Well, it just does. You're right. It doesn't hold true. We can't use we can't use it for those because it doesn't hold true on that. Let me turn that off. So same thing, 5 and 6. We can't use the extreme value theorem for 5 and 6 because the conditions don't hold true. Maybe that's more likely what I should say. but that doesn't mean it might have an absolute max or an absolute min. And if you look at number 5, notice there is a y value that we get back that's the smallest y value for g of x. And that's going to occur when x is a. So f of a, the y value is the absolute min. If I look at this at x equals c, this is a closed circle here, and that's the highest y value on that graph. And so f of c is an absolute max. And the last one, again, I can't use, it doesn't hold true. The conditions don't hold true to use the extreme value theorem, but it doesn't mean it doesn't occur. If I look at this though, there is no interval around my highest point in here. That's actually I'm kind of curious on that. I don't think that that has an absolute max. Well, let's go back to the definition and look really quickly. Okay, so let f be a function on a domain, then f has an absolute maximum value on D at a point x equals c if that y value is bigger than or equal to all y values in the domain of x and D. So according to that definition, this is the highest y value. It's defined there. So I think maybe we can then say that f of a is our absolute max. And then over here at B, not B, at C, we have the smallest y value. So f of c is our absolute min. Okay.
But the discontinuity prevents it from being true, right?
The discontinuity makes it so that that theorem doesn't hold true for that graph. So in order to use that theorem, it has to be continuous on a closed interval. So, but even though that theorem doesn't hold true for that graph, doesn't mean that it doesn't have an absolute max or absolute min. That theorem is just guaranteeing that there is one if our function is continuous on a closed interval. So we also have what are called local maximum and local minimum. And so you might hear this terminology, find your absolute extrema or local extrema. That's talking about your absolute maximum and absolute minimum. Definition, we say a function has a local maximum value at a point C within its domain D if f of x is less than or equal to f of c for all x contained in the domain lying in some open interval containing c. Okay. Same idea here. A function f has a local minimum at a point c within its domain D if we can say f of x, our y value, is bigger than or equal to our y value at c, f of c, for all x in the domain lying in some open interval containing c. So now knowing that, there's another couple of theorems in here. So we're going to use the first derivative test to help us find where these absolute maximum or absolute minimum occurs or local maximum and local minimum occurs. Remember, the derivative is telling us the slope at a particular value on our graph. If our slope of our graph is 0, then we know, or it could occur, that we have an absolute or local max or a local min. Could, not necessarily. Other place that this can occur, well, let me talk about this first, and then the next theorem would give it to us. So this theorem, which is the first derivative theorem for local extreme values, says if f has a local maximum or a local minimum value at an interior point C of its domain, and if the derivative is defined at C, then f prime of C is going to equal to 0. Okay, so it said that if the derivative exists. So here's a case where we have an absolute max, but notice that that's a sharp corner. And so sharp corners, it wasn't differentiable at those values, but it still has an absolute max there. So basically what we're doing, we're going to use our first derivative test. We're going to find our derivative, set it equal to 0, and find all those values that set it equal to 0. Those values which set it equal to 0, and one other place, are called our critical points. So an interior point of the domain of our function f, where f prime is 0 or undefined, is a critical point of f. So we're actually going to find our derivative. We're going to set it equal to 0, and we're going to find and see, is there any value in our derivative where it's undefined now? And if that value where it's undefined, we're going to call it a critical number. But it has to be in the domain of our original function. So if we have some continuous function on a closed interval, we can use that extreme value theorem and figure out what that absolute max and the absolute min are. So finding the absolute extrema of a continuous function f on a finite closed interval. So by the extreme value theorem, it has an absolute max, absolute min. First thing you're going to do is you're going to find all the critical points of f on your interval. So you're finding again where f prime of x equals 0 and where f prime of x is undefined. So once we've found those critical numbers, we're going to go back and we're going to plug the values, our critical numbers, in for x in our original equation f. So evaluate f at the critical points and the endpoints. So remember, we saw that our endpoints could be the absolute max or absolute min. And then we're going to look at our y values, and we're going to take the largest and the smallest of these values, and that will be our absolute max and absolute min. Okay, so now we get to go do the fun part and look at some examples and use some algebra to solve and calculus. So we're given an equation, f of x equals 4 minus x cubed. We're given that it's on a closed interval between x equals -2 and 1, and including those values. And we want to find our absolute extrema. And we want to graph this. So to find our absolute extrema, we want to find our derivative, and we want to find when our derivative is equal to 0 or undefined. And undefined. So taking the derivative, this one isn't bad, f of x. The derivative of f of x is equal to, well, derivative of 4 is 0, minus the derivative of x cubed is 3x squared. So we can say our derivative equals to 0. Well, -3x squared equals 0 when x is equal to 0. Our derivative function is defined everywhere. So this is where we want to test our values. The other thing that you need to make sure is that that critical number is in this domain. You might find some critical numbers that fall outside of the domain given, and it is in this domain. So remember, those local extrema or absolute extrema could occur at the end values of our domain. And so we want to test values, -2, our critical number is 0, and our other endpoint 1. And so plugging in our x values to our original function, we're going to see which x values give us back the largest y value and which one gives us back the smallest y value. So plugging in -2 wherever we see an x, we get -2 quantity cubed is -8. So we have 4 minus -8. So 4 plus 8, that's going to give us 12. If we plug back in 0, wherever we see an x, well, 0, so that just gives us back 4. Then we plug in 1, wherever we see an x, we get 4 minus 1 cubed, so 3. So our biggest value that we get back is 12. So we have an absolute max of 12 at x equals -2. Or we have that point, -2, 12. And then our absolute minimum value is 3, and it occurs at x equals 1. Or it's our 0.13. It wanted us to graph this. So we have a point -2, we have positive 12. At 0, we have 4. And at 1, we have 3. I'm wondering if to me, x equals 0 is probably a local minimum. And so my guess is, well, maybe not necessarily. It might just level out here. But it could come up, right, and come back down. So how could I tell if that did that or not? But if that happened, though, then I would have had a 0. No, I would have had it would have had another slope of 0. So that wouldn't have happened. So basically what's happening here is that line is flattening a little bit. I want to erase, okay. Kind of flattening in there and then kind of like this. We'll be in this chapter putting these tools together to help us graph these. It's just getting us started. So the next example says find the absolute maximum and minimum values of the function on the given interval, then graph the function, identify the points on the graph where the absolute extrema occur. And so we're given h of x is equal to -2 times the cubed root of x. And we want to look at the absolute extrema on the interval between -8 and 1. And so we want to find our derivative. And so before I find the derivative, let's rewrite this so that we don't have a radical. So this is -2x raised to the 1/3 power. So now we can use our general power rule, bring our power down front. So -2 times 1/3 is -2/3. X raised to the, so subtracting 1 from 1/3. 1/3 minus 3/3 is -2/3. So just rewriting this, cleaning it up a little, we have -2 all over 3, and we have the cubed root of x squared. So our critical numbers occur when h prime of x, our derivative, is equal to 0. Well, this is never equal to 0. Right? If I multiply both sides by my denominator, I'd get -2 equals 0, which is a false statement. So there's no value of x which sets it equal to 0, but we also want to look at the values where it's undefined. So h prime of x is undefined. And values which set my denominator equals 0. And that would be at x equals 0. But if I look back at my original function, I can plug in 0 for h of x and I get back a real number. So it's part of my domain and it falls in between -1, -8 and 1. So this is a critical number. So we're going to take our critical numbers that we found, which is just one of them, and our endpoints, and we're going to plug it back into our original function to see if we get the smallest or largest y value back. And because it's a closed interval, this function is a continuous function. By the extreme value theorem, it has to have an absolute max and an absolute min. So if we go in and we plug in -8, wherever we see an x, we get -8 quantity cubed, or the cubed root of -8, which is -2, times that -2 out front is 4. We have our critical number of 0. So if we plug in 0 wherever we see an x, -2 times the cubed root of 0 is 0. And the last one, if we plug in 1 wherever we see an x, an h of x, we get the cubed root of 1 is 1 times the -2 out front gives us -2. So we have an absolute max of 4 at x equals -8, and we have an absolute min of -2, which occurs at x equals 1. So we want to graph this. So at -8, we had +4. At 0, we had 0. And at 1, we had -2. We'll know more about our graphs later. About, the kind of the shape, the curvature, And the second derivative will tell us that, which is called concavity. But we gotta wait till a couple weeks from now to learn that. So our next example says find the critical points, the domain endpoints, and the local extreme values of the function. We have y equals 2x, the square root of 100 minus x squared. So let's first look at the domain of our function. So we do have to worry about values which give us negative numbers underneath our radical. And so we are looking at when is 100 minus x squared greater than or equal to 0. So there's a couple ways that you can figure this out. You can figure out the values that set it equal to 0 and find out where is our graph falling above or below the x-axis at those values. And I noticed that I can rewrite this as a difference of squares, 10 minus x all times 10 plus x, greater than or equal to 0. We can think about this. If I think about my function f of x equals, I'm going to write it this way, negative x squared plus 100. Think of it with transformations of graphs. Negative x squared tells me my graph is facing downwards, and that 100 is telling me I am vertically shifting it up 100. So we just graphed, if we graph this, those values, negative 10 and 10, those are the values where we're crossing the x-axis. And so we're looking at the values which are going to give us positive y values underneath that radical. And so that's going to be between negative 10 and positive 10. So our domain for y is from negative 10 to 10. Okay, so I have the end values of my closed interval where this is a continuous function. So now I want to find my derivative, and I need to find out where my derivative is equal to 0 and where it's undefined. So let's take the derivative. When we take the derivative, actually before we take it, let's rewrite it a little bit. This is y equals 2x all times 100 minus x squared raised to the 1/2 power. So derivative of y, we can write it as dy dx or y prime equals, so derivative of our first function, derivative of 2x is x times the second. The second I'm just going to leave in square root form. So times the square root of 100 minus x squared plus the first function, 2x, times the derivative of our second function. And so the derivative of our second function, we're going to need to use the chain rule. So bringing down our power down front of the inside, subtract 1 from our exponent, we get negative 1/2 times the derivative of the inside. And so the derivative of that inside is negative 2x. So we got some work to do to clean this up. So we have y prime equals the square root of 100 minus x squared. Notice that this 2 here in my numerator and 2 in the denominator cancels. In my numerator, I'm going to be left with an x times a negative 2x. So I'm going to put the minus out front.
Wait, why is it x times the square root of 100 minus x squared?
It shouldn't, that should be a 2. Thank you. The derivative of 2x is 2. Should I say that? I don't know. Thank you. Sometimes I just need to tell myself to slow down. Okay, so this is negative 2x here. All over 2x squared, because I have this x times this x. And then I'm going to bring this piece down to the denominator and rewrite it in radical form. So I have the square root of 100 minus x squared. So let's Well, I was going to say, let's just rewrite this as a single fraction, but I think we can solve this too without doing that. So this is undefined, right? There are places where this is undefined. But those places where it's undefined are actually values that are in our domain. It's our n values, -10 and 10. So it doesn't really give us anything else to check because we have to check our n values anyways. We also want to find out when is our derivative equal to 0. So we have 0 is equal to 2, the square root of 100 minus x squared, minus 2x squared, all of the square root of 100 minus x squared. Let's clear our fraction. Let's multiply both sides by the square root of 100 minus x squared. So when we do that, that square root times 0 is just 0, equals, when we distribute this square root of 100 minus x squared times that 100 minus x squared, those radicals are going to clear out and we're going to be left with 2 times what was underneath the radical, the radicand, 100 minus x squared. And then we have this square root of 100 minus x squared times this -2x squared over the square root of 100 minus x squared. So that leaves us with minus 2x squared. Let's distribute our 2. So we have 200 minus 2x squared, and then minus this 2x squared. We have 200 minus 4x squared. We can factor it. We can isolate our square and use the square root method because it's in that form. So if I do that, I add 4x squared to both sides. I get 4x squared equals 200. Divide both sides by 4. I get x squared equals 50. And then x is equal to plus or minus square root of 50. So x is equal to plus or minus. This is where we could use a linear approximation. We just learned that, but we're not going to. That's basically it. Sorry, past time. Square root of 50. This is 5 root 2. So I know it's about 7 point something. And I need to know, is that in my domain that we were looking at? And it is. So we actually have a multiple critical numbers that we need to test and are in value. So we're plugging it into our original function, y equals 2x square root of 100 minus x squared. When I plug it in, let's do smallest to largest. So -10. We know if we plug in -10, that gave us 0 underneath our radical. So that's just going to give us 0. If we plug in that -5 root 2, I'm going to do it as -root 50. If we plug it in there, we get this negative. Maybe I need to do some work. Y equals -2 root 50. All times, well, -root 50 squared, that's positive 50. So that's 100 minus 50, which is 50. That's nice. So we have -2, root 50 times root 50 is 50. So this looks like it gives me -100. If I plug in positive root 50, underneath the radical, again, I'm going to get 100 minus 50, which is 50. And so we get 2 root 50 times root 50, which is 2 times 50 is 100. And the last one, 10. If we plug that in there, we get back 0. So this would be our absolute min, and this would be our absolute max. Okay, so we're out of time. We pretty much went through all the different types of examples except for a piecewise function of doing 4.1 material.